Good morning, everybody. This is going to be the first in two or three videos that come at you this morning about hypothesis testing. So, in overall, hypothesis testing is kind of a logical argument, with a double negative conclusion at the end, but it's really just to test the likelihood of a claim. So, the way you test it is by taking a sample and see how that lines up against the claim, and I'll show you a couple examples of that. If the sample is reasonably similar to the claim, you have no reason to doubt its validity. And if it's not, you have to determine if it's dissimilar enough. And this is related to sampling variation, that there's a natural amount of sampling variation, but too much would indicate that there's more going on than just sampling variation alone. This is something you have to keep in mind as you go through this. At the end of all hypothesis tests, you arrive at a p-value, which is a probability. And it's counterintuitive, but low probabilities end up being strong evidence against the claim. And we'll get into that a little more in a bit. So here's an example I'm going to use, that a deck of cards is supposed to be half red cards, half black cards. Spades and clubs are black, hearts and diamonds are red. So one way you could study whether a deck of cards was just a standard deck of cards is, well, there should be half red, half black. We'd write that as the population proportion of black cards should be 0.5. The population of red cards should be 0.5. And that would be, if the deck would be fair if it sort of met all the characteristics as described before. But what if it's not? Suppose for whatever reason you thought a deck of cards was not fair, a casino was cheating or using rigged decks, you'd have to come up with evidence to show that it wasn't fair. So in hypothesis testing, we always start with two hypotheses, and the null hypothesis and the alternative hypothesis. The null hypothesis, and by the way, the word null kind of represents empty set or zero or nothingness. So it basically assumes nothing's strange, nothing's different, nothing's off. Like what has been stated to be true is true. What's thought to be true in the past is still true, or what's known about one group to be true, you sort of assume that's true about another group. And you'll see all these scenarios in different problems. In the deck of cards example, the null hypothesis would assume that's a fair deck of cards. No funny business. That's exactly like we'd expect. Half red, half black. If we were investigating this, the null hypothesis would assume that it's 50% red. So in the focus of this, we're just going to look at red, expecting the deck to be half red. So the null hypothesis would be that P equals 0.5. And if you read those symbols, it would really read null hypothesis, the population proportion is 50%. And that circle next to the H is actually a 0, not an O. It represents null or an empty set. The alternative hypothesis disagrees with the null. The null has stated a value, and the alternative suggests the true value is either less than, greater than, or not equal to the value stated in the null. So in the deck of cards example, we could see any of these three alternative hypotheses, that P is less than 0.5, P is more than 0.5, or P is not equal to 0.5. P is less than 0.5 would suggest that less than half of the cards are red. And these symbols would read alternative hypothesis. The population proportion is less than 50%. That would be called a left-tailed test because you're looking at the left side less than of the distribution. And P is greater than 0.5 would suggest that more than 50% of the cards are red. And that would be a right-tailed test. And then not equal to 0.5 would be called a two-tailed test because you're not really sure whether the deck is heavy on the red side, light on the red side. You just think it's not 50% red, and that would be a two-tailed test. So in this case, the wording that we're used is just we suspect the deck is not fair. So that would be that the alternative hypothesis would just say we don't think it's 50%. P does not equal 0.5. So after stating the hypotheses, which is all based in the scientific method, we would just gather a sample and then test, what does the sample say? Is it what we expect? Is it different than we expect? Is it statistically significant? So let's look at one example. If I said, let's take 20 cards, and by the way, 20 cards is the smallest amount of sample you could use to have this all be legitimate. And this is based on the success failure condition we've been working with, that you have to expect 10 successes and 10 failures. And since we assume the deck is fair, we'd expect half of those to be red, half of them to be black, so we'd expect 10 of each. So here's the deal. We've got these cards. I'm going to count. We've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 reds out of the 20. And this was just a random deal. This is a website that replicates a deck of cards. So that is a sample proportion, p hat, of 13 out of 20, or 0.65. We can now use this number. I'm sorry, we can set up a sin. I wish I could. I might delete this part, but I don't think I'm going to do that. But then now what our job is really to look at 0.65 is higher than 0.5, but is it statistically significant? Is it unreasonably amount of red? As in, is it beyond what just normal variation we'd expect? So to do this, we use the same standard error calculation we've been using of p times 1 minus p over n, take the square root. So it turns out to be a common standard error, equivalent to a standard deviation, would be 0.112, or about 11.2%. So this is what we would expect the distribution of all deals of 20 to be. Most of the time it would be very close to 0.5, but if you add that 0.112 and go 1, 2, 3 standard deviations away, then you'd say it's not really surprising or unusual to see values below 0.28 or above 0.72 or 0.2. This is kind of the reasonable range within there. So where's our sample? It's right, you can see right there. 0.65 would be, it looks like around 1.5 standard deviations above. So we've talked about that not being statistically surprising or unusual, but we can get more specific and look at the tail probability. And what we're looking at, this is a StatCrunch image, that if we enter all this, mean of 0.5, standard deviation of 0.112, the probability of a value greater than 0.65 would be about 9%. If this were a right-tailed test, we'd be done and just say if the deck is fair, there's a 9% chance that we would see a sample proportion as high as 13 out of 20 or higher. Because this is a two-tailed test, we must also consider equal extremes values in the left tail. It doubles the tail probability. So we say if the deck is fair, there's an 18% chance that we would see sample proportions as extreme as we did, as in that much higher or the equivalent on the left side, because if it's a two-tailed test, there's really no reason to suspect that it would be higher or lower. It could go either way. So recall our hypotheses. And 18% is less than likely, but it generally wouldn't be considered statistically significant, meaning not sufficient evidence. In this case, we fail to reject the null hypothesis. In other words, our deal was not so surprising. It's not wild to deal 20 cards and see 13 reds if the deck is fair. But that doesn't mean the deck's fair, because the deck could still be 60% red and 40% black or something like that. So we don't say that we've proven that the deck was fair. We just say our evidence doesn't show that it's unfair. It fails to reject the null hypothesis. So let's try again. Imagine I dealt another deck of 20 cards, or another deal of 20 cards, and it was all red. Every card in here is red. That looks a little more suspicious. So what we need to do is analyze the probability of this happening. So if we drew 20 out of 20 cards, I would be surprised. And does that disagree with our assumption that the deck was fair? How likely is it that we'd see 20 out of 20 cards, or a probability of 1? So the first thing I want you to notice is on this distribution, we can only see up to 0.83 or 83%. So 100% is quite a bit further to the right. So hopefully at this point you've started to see when the sample comes out beyond what you can see here that it's very, very unlikely. So down at the bottom you see this 0.000004. Really that's saying that this probability is essentially 0. Even if you doubled that and made it 0.00000008, it's still less than 0.001%, which is extremely unlikely. And it turns out that's actually equivalent to 248,756 to 1. It's very, very, very unlikely. So The low probability, this is another chance to say low probabilities are strong evidence against the null. A probability as low as that is statistically significant. Based on the assumption that the deck was fair, it's extremely unlikely to see 20 out of 20 red cards. So the logical conclusion is the deck isn't fair. The premise was wrong. So in that case, we can reject the null hypothesis and accept the alternative. The proportion of red cards is not 50%. So in general, just as a ballpark, p-values below 5% are considered statistically significant, but you have to be careful on each problem. It will tell you sometimes what the value is. They might say prove this at the 1% level of significance, meaning that p-value has to be less than 1%. Okay, I think I'm going to pause the video there. Well, we'll do one more thing and then I'll pause it and come back with an example for you. So when doing confidence intervals, just to sort of transition from topic 6 to topic 7, the focus is not about a population proportion. You don't claim to know the population proportion. You just have a sample proportion. You're building the margin of error, which hopefully captures the population proportion. When doing hypothesis tests, some value is assumed to be the population proportion, and the sample proportion is used as evidence to test the likelihood of that claim. In other words, the hypothesis tests are centered around a proposed population proportion, whereas confidence intervals doesn't expect to know anything about the population proportion. All right. Okay, just one more thing I want to touch on is that there's all these, the problem with proportion problems is there's all these P's, so I want to clarify which is which. So P with nothing on it, lowercase p, is the population proportion, sometimes written as P sub O, which indicates that's an assumed value for P. And this is the value used to calculate successes, failures, and standard error when you're doing hypothesis tests. P hat is the sample proportion. This will be used to determine the p-value, which is the probability of the sample based on the assumption of the population proportion stated in the null. So in summary, these three separate p's, lowercase p is population proportion, lowercase p with that caret over the top is called p hat and represents the sample proportion, and capital P is the p-value. I'm going to walk you another example for proportions and then another example for quantitative in just a second.